the Master's Science in Physics. And I'm going to present a review about a topic that is very interesting and it could be solved in a really elegant way with something that is called quantum field theory. Maybe all of you or some of you already know about quantum field theory, but if not, it's fine because I keep simple all the terms. So I expect that everyone understood these topics or will understand in this presentation. Oh. Okay. So this is the guide for these topics. I will start with an introduction about the paradox, the Klein paradox. Then I will do a conventional analysis with Schrödinger equation. We will see that nothing strange happened in this framework. Then we go through a relativistic analysis. Particularly, I will use Klein-Gordon's equation. It can be done with Dirac's equation. I only state that and don't present because I don't want to talk about spinors and all those things. So I only state from the case of Dirac's equation. And then a possible solution. You will see that this topic is very normal in quantum field theory, but there are, in recent times, there are several papers about this topic. That's interesting because even it's something basic, someone could say, there are investigations about this in recent time. So first, what is the Klein paradox? Well, we start with something very simple, a potential. When we study the Schrödinger equation, we start doing all the calculations by doing everything about a system, and the system in one dimension is, how can I say, it's represented by this potential. So what is a potential? It's simply a potential step, and this potential, what is modeling? It's modeling electrodynamic potential. Essentially, it's an electrostatic potential. So it's very basic, it's very simple. But with this model, something strange occurs when we are dealing with relativistic particles. So in the Klein-Gordon, we will see that. And here I state that if we compare those solutions with the Schrödinger and the Klein-Gordon, we will find something in the probabilities that we will never see in the Schrödinger equation. So this will arise only in the relativistic part. And the problem is worst if we consider Dirac equation, because in the Klein-Gordon, it's strange, but well, it could be explained somehow, but in Dirac, it's totally a mess. And finally, we present, as I said, a solution. So the conventional analysis, this is the potential. We have a particle with mass m and charge e. So this E0, it's constant, and it's nothing but the fundamental charge E times this electrostatic potential. So all this is well known, and we start doing regular calculations. We took Schrödinger equation, and we put a condition. We said, well, we start our experiment by sending a particle to this potential from the left, your left. So the particles coming this way, and we expect two types of things happening: reflection or transmission. That's all that can happen. So in the Schrödinger equation, the solutions are plane wave types. And here I impose that the particles coming from your left, so it's normalized to 1. And this is the amplitude of reflection. So the square, the modulus square gives us the probability that that particle gets reflected. And here, T tilde, it's something similar to the transmission amplitude, but because we have two types of wave numbers in the left, it's basically free space, and in the other case, we have the potential. Then this is not exactly the amplitude of transmission. We will see that later. But here, simply by considering the wave number of the left, this is simply math, solving the Schrödinger equation. And Q is the wave number from your right. So nothing new. Imposing that the wave function is continuous in the interaction point, that's the origin, the continuity of the wave function and continuity of the first derivative, then we can find, as I said, the reflection coefficient, that's the probability that the particle reflected, or the transmission by simply imposing conservation of probability. That's say the sum of the transmission probability plus the reflection gives 1, nothing more. So here I use notation. I said that the wave number from the right divided by the wave number from the left, it's simply raw to simplify everything. So we have reflection, transmission, and we analyze these two things. What happens when we have large energy, lower energy? So if we send a particle that its energy is greater than the potential, then we expect that some probability, with some probability, the particle reflects, and with some probability, the particle is transmitted. And it's stated in this figure. The behavior of T and R, it's symmetric. And when R tends to 0, the transmission tends to 1. So nothing new. And the other case is when the energy is less than the potential barrier. In this case, as in this part, we are saying that rho is equal to Q over K. And remember, Q is equal to this. If we take the square root, then when P is greater than E, then Q is imaginary, and it's purely imaginary. That's important. Because it's purely imaginary, here we can take the I out, and this expression, we need to take the modulus to be correct, and it's 1. And when we rest 1 to 1, we got 0. So when the particle have less energy than the potential, always we have reflection. Nothing new. But now we are going to use Klein-Gordon's equation. I will not deep in this equation, but it's simply the Einstein's relation between energy and momentum being quantized. So the momentum is quantized, and here we have, again, the energy minus the potential. So we can solve this equation in an old-fashioned way, making the simplest. This is constant because the potential is constant in a region, it's 0 in the other. So the solutions are exactly analogous. We have Q and K, but we have now this term that's coming from here, okay? So again, we can make an analysis of the energy being greater than the potential and vice versa. But I propose something that it's, I guess, more interesting to see how this behaves. And it's instead of taking the energy of the incident particle changing, we take constant energy and vary the potential, because in experiments, it's easier to change the electric potential in general. So that's why I stayed here. Okay, so now again, we are searching for the behavior of this row. And you can do it by yourself. It's inequalities by seeing what sign does this multiplication have. But I make it simpler and I present the variation of the potential instead of the energy. This is the domain of the potential. So if we have a potential less than the energy and less than E minus mc squared, then this row is real because we have two positive numbers multiplied, then it's positive and it's real, okay? So in this part of the domain of the potential, it's like the old result. We have the potential, and here we can plot the reflection probability. So in this part, the reflection will start if the potential is 0, then the reflection never occurs because we don't have a potential that can reflect the particle. Then it starts to grow to reach 1. The probability of reflection is 1. But in this part, we have something strange because in this region, it's again like the Schrodinger equation. If the height of the potential is between E minus mc squared and E plus mc squared, you can see that one is positive, the other is negative. So the rho is imaginary, purely imaginary. So we have R is 1. But when the height of the potential is really, really big, then again, we have two negative numbers. So again, rho is real. And this is why I say that this is strange, because how could it be that if the potential increases, then we get reflection, the reflection is less than 1. This doesn't have sense because if we expect that the reflection already is 1, then it will be 1 no matter how big we take this potential. And that's what I said here. I explained it already. And I present a numerical case. I take the energy is here. I take it over mc squared, 1.3, and I plot it for this equation 7. And not only it is less than 1, it oscillates again. It increases from a threshold, and it continue increasing. So this behavior is strange, but it gets weird when we take the X equation. I only put the rho, and the rho is this term. You can do it by yourself. But now, if you remember, when rho is real, it's always positive. But now, if rho is real, from this factor here, we can have rho negative. So this implies, by inspection of or expression for the probability of transmission, it's less than 0. And how could that be? And for R, it's greater than 1. So there are something strange if we take the Klein-Gordon or the Dirac equation and solve these equations by one particle. So that's what we see in the slides. But now I want to present you a possible solution, but Um, Before doing that, I want to present some recent research about this. This is a research about the resolution of the Klein paradox, but doing only one particle dynamics. It doesn't put the quantum field theory, and it's strange, this paper, because uh, it solves the problem but doesn't say anything. It's like only doing a logical explanation but doesn't explain experiments, nothing. So here is the paper if you want to check it later. This is another from 2020. And this paper says that we don't have any paradox. The behavior of the reflection decreasing, it's well explained, and we don't have paradox. But that it's a naive explanation, because in this paper, he do it some similar graphs, not exactly the same. And he says it's totally normal. We only need that the reflection doesn't get greater than 1 or less than 0. And it's a possible solution, but again, it's strange, at least. And finally, this is the paper that I took to follow the solution. Hansen and Randall said that, well, we need to take account the quantum field theory to solve actually the problem. And if it's the case, with experiments, we can see that the quantum field theory is actually correct. So how this solution starts? By taking the framework of Feynman. We say that the antiparticles are only particles that are traveling backwards in time. This is the state. If you work with Feynman diagrams, I will draw a little in a minute. You can know that antiparticles have this momentum that it's minus the momentum of the actual particle. And again, the solution that we somehow compute in the previous slides take the account of one particle dynamic, but here the solution will be in terms of the states of particles and the states of antiparticles. This tilde, it's the representation of a state of antiparticle. And what is B and D? Well, B and D are the creation and annihilation operators. Well, the creation are the daggers, and the annihilation are without the daggers. So B is the creation for particles and D for antiparticles. And I made a state that E implies that the particles are moving through, going from far away through the potential, and without the particles that are reflected, so or antiparticles. So I start with saying, well, because we are dealing with quantum field theory, what's the probability or the amplitude probability that the vacuum remains vacuum in presence of this electrostatic potential? And I will state that this probability is e to the power of iw, and w is an imaginary number. Then we can say, well, if this is the amplitude of probability that the vacuum remains vacuum, what is the probability that we don't send any particle through the potential? We only say that if the potential is there, what is the probability? Oh. Well, what is the probability that a single pair particle-antiparticle creates from the presence of the potential? Oh, thanks. And the amplitude of probability is simply this term. And what's the meaning of this term? Well, we said that we are creating a pair, and from Feynman diagrams, I will draw it in this part. the creation this is the time, and this is x. So this is antiparticle being created. So I draw the arrow in this way, but because it's moving backwards in time, actually the antiparticle is moving that way. So in, and this is actually yes. So that's that probability, amplitude of probability, sorry. And then if we have this one pair creation, we can use here, if you see it, it's not this, but we can use, if you know something about the theory, the Bogoliubov coefficients. If you don't hear, if you hear this thing and it's strange, the Bogoliubov transformation, it's nothing more than if we have a pair annihilation creation, the commutator is 1, and the Bogoliubov transform this into another, let's say, not A, B, B dagger. So it's a canonical transformation. And with the Bogoliubov transformation, we can say that that B that we have that I have here, it's nothing that this transformation. It's term and transformed here. So this out and creates, so this cancel out, and I state that the probability of the vacuum remain vacuum is E. So nothing complex. And from n pairs, the calculation are straightforward. You can do it, but it's nothing but this is the power up. Now, if we have pairs, particle-antiparticle creation, now this happens spontaneously. We don't need to have something else happening, but we need to account that the potential is there. The potential is there and it's not changing. Now, with that in mind, we can make the unitary of the probability. It's the sandwich of this amplitude of probability. And we are working in the Hilbert space of square insumable functions. So we need to calculate this series. And if it's familiar to you, it's nothing that an harmonic series. So because this series converge, because this is less than 1. So the result is this, what? Because it's -1. And we have, I tell you that this is an imaginary number, so the modulus of that is simply e to the power of -2, the imaginary part of omega, or w. And then we can state that this part, this imaginary part, is equal to this term. And it's important to state that it's less than 1. So now we are considering not only the creation, annihilation of the creation of particle-antiparticle, we are now saying that if we send a particle, what is the amplitude of probability that the particle reflects without nothing created particle-antiparticle. So this probability is calculated in this way. Again, with the Bogoliubov transformation, we can reach this part. And now the crucial part is to say, well, we calculate the probability of this without any coming in, and the probability of time on x without any creation on particle-antiparticle. Now we are interested in something like this. Okay. So the amplitude of probability that the particle reflects with n pairs created, pairs of particle-antiparticle. And again, invoking Google Evolve, the expression that we obtain is this. And finally, the not the tricky part, but the elegant part is that when we calculate the total probability of reflection, taking into account particles and antiparticles, then we take this series and see what does this series converge. So I already put this expression in the other slide. So it's the square of this, and this we have to look identically like this. So it's the square 4, and this series converge or don't. If you see carefully, actually it converges, and you can calculate it if I can state it to see something familiar. I can put it. So actually, it's simply um, uh, how can I say it? The derivative of an harmonic series. So, sorry, see, geometric series. Yeah, sorry, I mislead the names. And making algebra, simple algebra, we reach that the total probability is actually 1. So when we take particles and antiparticles, the probability of reflection is 1. So we sorted the paradox in an elegant way using quantum field theory. There is one thing that I want to say before closing this talk. When I was studying this, I talked with the Professor Nesterov. One of you already know him. And I say to him that, well, this solution is elegant, but the experiments must talk, because if the experiments don't see this particle and the particle creation, then the solution it doesn't matter. So it's only mathematics. But he sent me some papers about graphene. I don't know if some of you are well known this thing, but in graphene, actually, there are some experiments that confirm this explanation. But not only that, there are other authors, recent published papers about saying that it's not paradox. We don't need to do these strange things, because this author says that we can totally live with this this phenomenon. So it's really strange that recent research are focusing saying that it's not a paradox. It's something that happened, and call it Klein tunneling. But you can search it if you want. I have the papers, and you can come to me to read. And that's the bibliographies. That's all. And if there's any questions, I can present a paper. This Dragoman, it's strange. This guy, all the paper is about saying that no, we don't have paradox. I don't understand that part. Yeah, you can read it if you want. I will send you if you text me in email. Yeah.
It's a good point to you mentioned that for any, I would guess that for any even very nonsense statement, you will find a paper.
Yeah.
So I think one has to look for use, I say, to check the credibility of the paper or the author or making comments.
Yeah, I present this because I read it and I don't find anything like, maybe I need to say that all the text say nonsense. It's not something that you need to take seriously. You should not take it seriously. Yeah. Sorry. I find it in archive, so maybe not. Yeah.
And which year it is?
Oh, so 2010, I guess. This doesn't have. Yeah, 2010, I guess.
Okay, I don't need that.
Okay.
Now, if it is 2010 and in 15 years it won't publish it anywhere,
No.
that means
Yeah.
it's shit.
No, in any case, I mean, there are different ways to check if you can trust to papers, right? So of course, the easiest thing is that the paper would be published in a journal with a reviewing system, and even better if it is a well-recognized journal.
Yeah. A little comment. I took this paper from. It's cited in another paper that is published. So maybe
another point is, I mean, it's just for the benefit of the students, right? Another thing what you can do is check the author and where does he work, and if he has this, well, he might be on Google Scholar or on some other referencing system, and so you can get some idea how likely it is that reasonable paper or whether it's just different kind of rubbish.
This citation you are talking about is a self-citation?
no, it's not self-citation.
But the paper which cited it, where is it published?
Let me check. I have it in Google Classroom.
Because paper who cited.
Yeah, it's this paper. So I want to make sure if it is this. Yeah.
This is published where?
No.
It's not also published.
It's a lecture.
Yeah, it's a lecture.
So it's not also published.
Yeah. I check it in archive, but
There's no.
well, that's just definitely. Well,
It's not it's a reasonable.
Reasonable journal.
not highly, right?
Yes.
This is not. I mean, as
If you
Publisher
want
of
it, I
IOP.
can send you this paper. So for further discussion, I can send you if you want, but if you don't want, then if there is another question.
Yes, I have a question.
Okay.
This Klein tunneling is somehow experimentally measurable, you know?
Yeah.
It's not real. So there's no paradox.
No, the point is that if you call it a tunneling or not, right?
Uh,
Because what you can measure is the reflection probability and transmission probability. That is what you can experimentally measure. Now the question is that what will be the explanation? Will you call it a tunneling or you will call it a spontaneous particle-antiparticle?
Okay, I got it.
I mean, I didn't really understand the physical process where you get, say, transmission while you expect reflection. I mean, when the field is too strong.
Okay.
Or does it just mean that the particle will not cross, but you get spontaneous cannot be, right? You cannot get the spontaneous creation of
No, because we have conservation of.
particle and antiparticle.
Okay. Yeah.
Or what is the physical meaning of Klein-Gordon?
The physical meaning. Yeah. Okay. That part, the Klein tunneling that I told you in the last part, in graphene, they don't take exactly the same potential. They make an approximation with it's not this potential. They take it like this, that you already know. So from that we have common tunneling. So
No, the question is, if I have a tunnel, right?
okay.
And if I have no tunneling for a given potential width, and I increase the potential width, suddenly I have started having tunneling that makes no sense.
Yeah.
Right. Now, if I have a higher potential width, have a higher potential, then the probability of a vacuum change to antiparticle and particle increases.
The probability.
How it is? There are higher flux of particle and antiparticle. That depends on your potential width.
Okay.
Right. If you have a very low potential, you do not have vacuum do not change to particle and antiparticle. And if you have higher potential width,
Yeah, relativistic.
then relativistically you have a higher flux of particle and antiparticle from vacuum. Right. So that theory makes no sense.
Okay.
So the particle does not really tunnel, rather gets reflected, but you get spontaneous creation of particle
Antiparticle. Yeah.
which it could also not, right? Because it's static.
Yeah.
But of course, I mean, this is yeah. There are other questions about that. There are many problems, right? One is plane waves. They are not. You cannot create particles or antiparticles. You cannot do field theory in plane infinitely plane waves, infinite plane waves. And of course, also discontinuous potentials are not the best candidates for quantum field theory. But it's of course it's interesting to ask to what extent useful. And if this means that equations are wrong, the instruction of the field theory, or if it's just too unrealistic to have such singular potentials. So one should try maybe to have regularized
The potential.
differential and
Model. Yeah. Sure.
even then it's somehow yes, to really understand how we talk to
Yeah.
the
The
solution of the field equation.
yeah. I use Google Go for help. Transformation.
It's a very nice talk.
Thanks.